Hello, everyone. Welcome to this lesson today. So, in this lesson, we'll be looking at chapter 6 in our Building Autonomous Agents for the Enterprise series. So, building application with autonomous agents for the enterprise. So, that is the topic we've been looking at. We've started with what are agents. We define them as autonomous system that can plan, you know, reason and act on their own and solve problem uh, without human supervision. So they are advanced, generative AI, and they are built on top of generative AI with generative AI and large language model as the foundation model. So we've looked at design pattern, different design pattern. We've looked at we also look at orchestration. We looked at UI and UX design, putting the user into consideration when you are designing, not just design architecture, also design for people that want to use the agent. And then we also look at tools, how agent call tools based on context to solve problems. And so in this lesson today, in this lesson 6 of the series, we'll be looking at AI agents, knowledge and memory system of AI agents. How does agents reason and act based on what they know? We've talked about memory, we've talked about short-term and long-term memory. So we'll be looking at those systems in detail. What are memories, and how does agent use memory? Then we'll also be looking at knowledge and knowledge graph. So how is knowledge graph constructed for agent? How can agent recall what they have done before, or how can they use knowledge base in an enterprise? So enhancing agent utility through grounded facts and interaction continuity. So this normally prevent agent or any generative AI from hallucinating. When you feed the agent or the generative AI with a knowledge base, then it can augment whatever it's giving you with the knowledge base and then refine the response using the knowledge base, and then it gives you a very accurate response instead of hallucinating. So knowledge base is a system of reducing agentic hallucination in design. So knowledge and memory, that's chapter 6. So we are going to explain how agents become more useful when they can know relevant information and remember past interaction. So in the first section, we'll be looking at knowledge. In the second section, we'll be looking at memory. And in the third section, we'll be looking at outcome. So from the definition, knowledge gives agents access to external facts, documents, policies, logs, and domain content. So if you are building an agent for a specialized domain, you can't use general knowledge to train the agent. No, it's going to give irrelevant information. So when you are building an agent, make sure you build a knowledge base for the agent so it will give answer or it will solve problem based on the domain knowledge. For example, you want to build or design an agentic system for a legal system. You can't go and use the knowledge base of a medical system to build that. No, because what you'll be getting is hallucination and medical information which will not be relevant to somebody in legal system that want to use the agent. So that is the essence of knowledge base. It gives the agent factual understanding of the domain it is designed for. So it gives the agent a broad understanding of the problem it is designed to solve. So if you are designing an agent for a legal system, then you need a legal knowledge base. You need their policies, you need their documents, you need their domain content, their logs, and everything. So that's how knowledge base works. The memory gives the agent continuity by storing previous conversation, tool output, user preference, and task history. So memory is what allows the agent to reason actually. So it gives the agent, a knowledge of its background, And so when it stored the knowledge of what it has done in the past, it can use that knowledge to also help improve the the further problem it's going to solve later. So knowledge allow the agent to learn from what is useful and from what is not useful in order to uh, improve itself. And in memory, allow the agent to reason, to think based on past experience, and then improve based on what it has learned using reinforcement learning. Outcome: support better context engineering, making agent more grounded, personalized, and reliable. So, outcome is just based on context engineering. Context engineering is, giving the agent the right information that is needed at a particular time, or a particular situation, or a particular prompt, a particular, problem that the agent needed to solve at that particular time is the context, and it must be grounded. So it uses memory. It draws information from the memory, and then draws knowledge from the knowledge base to augment what it has in its working memory, and then act solve the problem based on the context at hand and generate response. So that is how it uses knowledge, memory, and context together at the same time to solve problem. So knowledge versus memory. So how can we differentiate between knowledge and memory? Knowledge knowledge is stored in a database. Memory can be short term, long term, can be episodic, can be working memory, can be any type of memory. We have four major type of memory actually. So knowledge are factual or domain specific information the agent retrieve when needed, such as policies, products, category, and technical documents, as we have said. And then we have what we call the knowledge base or the vector database, where this knowledge are stored and vectorized using a machine learning model. So an example of such database is Weaviate, and for a RAG database, that's retrieval augmented generation, we have like open source Chroma DB, or you can use cloud platform like AWS, Azure, and Google. Memory: the agent history. It includes previous user exchanges, prior to result, task state, and preferences. So memory is the history of what the agent has done in the past, and how it does them. So the history of the responses it has generated, the problem it has solved, the steps it has taken. Those are the memory. So they can be episodic, that's in form of episode, or long term, step by step. It can be procedural, or based on what it has solved using the steps and the planning. It can be short term, which is just for immediate response. It keeps such knowledge temporarily and then discard them when it is no longer needed. It can be long term as well, and so on and so forth. Then we have context. So memory stores useful context, which context engineering decide what to bring into the model prompt at the right time. So agents or agentic memory always store context. Context is the useful the information that has been useful in the past to solve problem, or the information that was passed into a tool to call a tool to solve the problem. So it uses context engineering to store all these context in the memory and call them whenever they are needed. Context windows, simplest memory. So what are context windows? So context window are information passed into the model during a single call. So single information is passed at at a single time or during a single call. So context window is the information that is passed to solve a particular problem, or the information that is passed to know the tool to call to solve the problem. That's the context window. Then we have rolling window. Rolling window keep recent messages, removing older ones when the token limit is reached. So rolling, just from data engineering, you we have tumbling window, rolling window, and so on and so forth. So rolling window here is just like the rolling window in data engineering. So it rolls information over and remove older ones that are no longer needed when the token limit is reached. So this is also a way of minimizing token usage. Implementation. So contests are very easy to implement, but important information can disappear once it falls out of the window. So if important information falls out of the window, for example in rolling window, you can no longer retrieve them. So that they are easy to implement, but you must be very careful how you also program them. Lack context limits. So large windows help, but model can still miss details inside very long prompts. So make sure your prompts are short, and you can make them long when the situation demands it. But short contests are very very easy to manage. But when the contests become too long, or some details may be forgotten. For example, in agents, they use what we call fussy algorithm. They pick, the first thing at the beginning of the statement and the last thing, and they use that to answer the question. So whatever is in the middle is normally overlooked. So make designing context to be specific, to be short, and to carry the information that is needed is very very important in agentic system design. Alright, so traditional search and semantic memory. So what's the difference? So traditional search uses what we call keyword matching. So it uses keyword to search for information in the database. For example, we have a method like BM25. It is very good when the user query contains exact or specific terms. So these are very useful when you want to search for exact information. You need factual information like 100% accurate. So you can use a traditional search, which is also called the keyword search. These are also used in vector databases. Vector databases are a way of storing vector using what we call cosine similarity in a vector database like Weaviate. An example of them is Weaviate. Then you can search for key terms using keyword. So that is called traditional search or method. Then we have semantic memory. So for a semantic memory, you have to use what we call embedding. Embedding is a way of storing information using cosine similarity in a vector database or vector store. So vector store, you use embedding and vector store to retrieve information by meaning, not just exact words. So in semantic memory, you are not just using keyword, you are using the vector store. You are using the dimension or the positional coordinate of the object in the database to also get the information apart from the keyword. Then when you combine semantic search and traditional search, then you have what we call the hybrid search. Okay, is a method of searching a vector database which is discussed in vector database. So maybe one of these days we'll do a video on that, and then you learn more on how to design and search for key terms in vector database, and also do what we call the semantic search, and then combine them together to have what we call the hybrid search. Vector stores. So vector stores allow agents to search large knowledge bases quickly and return relevant context for better answers. So just as I have said in under semantic memory, which uses embedding and vector store at the same time, so vector stores own or uses the positional coordinate of the object to search for the object in the knowledge base, and it gives exact response of what it corresponds to. And if it doesn't know, you can program it to say if the object is not found, return I don't know. So that is how they work. So or then we have another one here, which is retrieval augmented generation, RAG. So it's a very, 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 very important topic in generative AI and agentic AI system, because it prevents LLM from hallucinating. It prevents them from, beating around the bush or generating inaccurate information. It prevents agentic system from assuming what is not right. Do you understand? So RAG is one of the most important knowledge techniques of agent. It is very, very, very important in generative AI system design and agentic AI system design. So step one, how do you build a retriever augmented generation? Take note, retriever augmented generation uses what we call vector database to store information. It uses semantic embedding or embedding by chunking, embedding, and storing the information, and then the LLM can retrieve the information whenever it's needed to augment every or whatever information it has in its short term or other memory, and then generate response. So that is how this works. So retriever augmented generation, from the name retriever, the LLM retrieve information from the database based on the context. Then it augments whatever it has from other information, from such short-term memory, or from long-term memory, or from other website APIs and wherever. Then it now generates response, accurate response to the user. So that is how it works. Retriever augmented generation. Get the information, add it to the information, get the right information from the database, add it to the information in the memory, then or validate and generate response. So that is how it works. And then we have the steps on the slide here. Step one. So when you are building a RAG system, I did not put the other steps here, but as a data engineer myself, so what you do is you ingest the data from whatever it is. You have your processing unit. If the data is not yet processed, of course, I'm a data and AI engineer, so I can do both. What you need to do is to get your data from wherever it is, maybe from domain, from website, from other databases, from textbook. You've gotten your data, you've splitted them, you've designed them, then ingest your data, clean and process your data. Make sure there is no duplicate. Make sure the quality is perfect. So clean your data, deduplicate the data, or ensure the data is very, 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 very clean. So quality is very, very important when you are building a RAG database. So when you've cleaned the data and transform it and clean it, then you store it wherever you want to store it. Then from there, you can now start split the document into chunks. So split the data into chunks, okay, using your Python code and any LLM API like OpenAI API. So split the document into chunks. Number two, convert chunks into embedding. So when you chunk the document, you convert the chunks into vector embedding. Okay, that you embed them using vector, that is in a vectorized database. Then you store the embedding in vector database. After embedding, store the embedding in a vector database. For example, you can use Weaviate or ChromaDB, or Azure, Azure AI Search and AWS and the like. Then step four, retrieve relevant chunk at query. So when the LLM receive a user information, it generates context from it, and then go into the vector database and retrieve relevant information, okay, using query. Then it pass context and question to the model. So pass question, context and question to the model. After retrieving the information, then it pass the context and question to the model, that's to the brain of the agent, and then better use case. So these are the use case. So after retrieval, it pass the context and question to the model, then the model in turn or augment the information and generate response to the user. So that's how agentic system uses a RAG database. The information, the document must be chunked, it must be embedded using vector embedding, and it must be stored in a vector database, and then the LLM can now retrieve and use it to augment whatever information it has in short-term memory, and then generate a response to the user. So best use case, better for dynamic or private knowledge. So this is used for dynamic or private knowledge, like in a legal system, in a medical system, where accuracy is very, very important. RAG database are used there. Applications. So it can also be used in, you know, in security to for policy, you know, divination. So you can store policy in a RAG database and feed it into an agentic AI to implement you know, this policy as a guardrail to other generative AI or any agentic AI built in the company. So it can be used as manual or document. Right, so that's that about RAG. Now let's look at semantic experience memory. So enabling agents to remember and apply past interaction across different user sessions. So semantic experience memory. So how does semantic experience memory work? Remember in the previous slide, it says semantic experience uses embedding to retrieve information from a vector store in order to, you know, augment information. So number one, we have a semantic experience memory allow agents to remember past interaction across session. So semantics, so you can call it, you know, episode by episode, scene by scene, section by section. So it allows the agent to remember all the past interaction and the time those interactions were made or stored. Then embed and retrieve. Inputs are embedded and stored. So this past interaction or context, they are embedded as well, and they are stored in vector database. So when a similar task appear, the agent retrieve related past experiences and add them to the prompt for context. You understand? So it's stored this past information sections or information from sections that he has had, the context and everything. It embed them and store them in a vector database, and then it can retrieve them whenever there is a prompt for such context. You understand? Then personalized adaptation. So personalized adaptation helps agents become more personalized, adaptive, and consistent over time. So semantic memory, in short, enable the agent to generate personalized information uh, in a consistent manner. So semantic search go into the or using semantic search or semantic memory, the agent goes into the memory and generate extract or personalized information based on the user context, because it has stored all the information that you need. And this is how all this Claude GPT works. When you store your information in your session, so it is used to your way of, you know, answering question. All your informations are there, so instead of just hallucinating, it goes into your memory, into all your sections, and then answer you quickly, or using your, you know, your preferred format. And so those are semantic memory. Then we have knowledge graph. Remember we just talked about you know, RAG. So we also have knowledge graph, and knowledge graphs give birth to what is known as graph rack. So what are graph graph? Let's start from knowledge graph actually. So entities, knowledge graph stores entities as nodes, relationships as edges, and connected meaning across and connect meaning across them. So knowledge graph are just graph databases like um, Neo4j, Apache Gremlin, um, Amazon Neptune, and we also have the graph database on Azure. I've forgotten the name now. So Azure Graph database is also there. So these are graph database. They store entities as node and relationship as edges, and connect the node and connect the entities and the relationship together using nodes and edges. So they store information in nodes. They use fuzzy algorithm to store information in nodes, and then they use edges to connect those nodes together, and it's help the database to map or write information to the right context or to the right entity, thereby generating accurate information. So graph rag improves on normal rag using a knowledge graph instead of only document chunks. So instead of using document chunks embedded in a vector store, it uses knowledge graph. It uses these informations and entities collected and stored in nodes and edges, because it is easy to connect entities to what it is related to, and it links them together and quickly generates accurate information. So graph rag is, I would say, generate more accurate information than rag itself. But both of them are also good, but they have specific use cases. So multi-op reasoning. The agent connect facts across multiple sources. So this graph rag enable agents to connect facts across multiple sources using mapping entities to context. GraphRag utility. GraphRag is useful when questions require relationship, understanding, or connecting scattered information across a large data set. So that is when it is useful. If you have very scattered information, RAG is used for structured information that you can store in a database. But for RAG, you have a scattered information that you cannot be that cannot be easily chunked. So you can design a can split them into entities and connect them using relationships, and then you can uh, develop a database from there and use it for the agentic system design. So how do you design a knowledge graphs? So a structured approach to creating graph-based domain knowledge. So you can follow this structured approach. The first thing to do is to collect data. So collect data from various sources like body tests, like websites, like social media, and so on. So provide context or explanation to support visual headlines. So the first thing is to gather your data, perform data collection. Then after collecting data, clean the data. Okay, clean, process the data, remove duplication, remove unrelevant informations, and make sure the data quality is good, because it will help you have a a good graph database or a good knowledge graph that you can use for your graph work. Then, after cleaning the data, you do entity recognition. So, sample body test providing context or explanation to support the feature or headline. So, we have this tool in Azure AI Search that you can use to do entity recognition. So, you recognize all the entities in the clean data, in the information. So, and the entities are stored and registered. Then relationship. So after finding the entities, we build a relationship between them. So sample body test providing context or explanation to support the visual headline. So build relationship between entities and the intent. So connect entities together. For example, you have a car. Where does a car uh, ride? where does a car move, that's on the road. So you connect car to road, or you are traveling from US to UK, maybe you want to take a flight, or you want to build an hotel. That's what, all those are entity. It connects them to intent and to relevant information. And then we have ontology design. So sample body test providing context or explanation. So you design ontologies. That's also building relationship between the entities and all these uh, information that you have there. And then you populate the graph. So after entity recognition and building relationship, the next thing is to populate the graph database, and then you integrate the graph database into the agentic AI system, and then you have your ongoing information. So the information can be retrieved and used to augment users prompts, and then generate responses to whoever needed. So these are just example. For example, you are building for this, you generate this particular information, and then it become a very good output. Right. So then we have dynamic knowledge graph. So managing real-time information update in fast-changing enterprise environment is very, very important. And therefore we have dynamic knowledge graph. So how do you ensure your knowledge graph is dynamic? The first thing is continuous update. Always update the knowledge graph when there is a new information, and make sure the data is clean and the entities are instructed. So dynamic knowledge graphs are continuously updated with new information. Fast changing domains. So powerful for this is very useful for news, finance, medicine, monitoring system, social media, life enterprise operation. So these data are collected from fast changing domain that are dynamic, like social media, like news, like finance, and so on. So and that's why you need continuous update of the knowledge graph or the graph database. So identify risk. So higher maintenance complexity, resource cost, privacy concerns, security, and over reliance. So do not over rely on knowledge graph. Identify risk. Know when the knowledge graph is needed, and when it is not needed, you can use a RAG database instead. And then make sure you implement privacy and policy. Make sure the data is secured, and make sure you collect only the information that you need from the social media, from the finance API, from the finance system, or from the medical platform. So human oversight remains important, very, very important here. So to you know be ethical in whatever we are designing. Long context and index free rack. So what are long context and index free rack? We've talked about long context at the beginning, where we said that long context can be mismanaged by the agent when the context is too long, and when the information is contains is irrelevant at times. So evaluating the benefit and trade-off of very large model context window. So direct long context processing. Newer model with large context windows process huge document directly, reducing retrieval need. So when you have long context, RAG database may not be needed. So because the agent can process the information directly without retrieving any information from the database, because the context become a prompt. So instead of using a simple and simplified context to retrieve information from the database, because the large context is too large, and it cannot immediately read a single meaning or generate a small useful information that will map to the database. It just generates the response without retrieving any information from the database. Long contest trade-offs. So long contest can be expensive, slow, and the model may still miss the most relevant detail. So they are very, very expensive and slow. It may involve a lot of token usage and all that, and may even generate irrelevant information and make the agent to hallucinate. Recommended approach. So make sure you combine long context models with selective retrieval for better cost, precision, and accuracy. So to ensure accuracy, do not over rely on long context. So you can, do them 50-50. 50% of long context and 50% of RAG, so to ensure that you minimize cost and you also generate precision and you build a system that is accurate. So note taking for reasoning. Does agents take notes? How do they take note of what they have done in the past, the plan they have made, the reasoning and the action they have taken? Do they take note of it? Yes, of course they do, because that is why there is short-term memory. They keep those information in working memory so that they will retrieve them or refer to them whenever there is need for it. So note taking is another memory technique where the model first generates notes about the context before answering the question. So it helps the model to reason deeply. Okay, so by summarizing or highlighting important details before producing the final response. So it helps the agent to also think whether the what it's trying to generate or what it's trying to process is actually accurate and perfect. They're useful for complex reasoning and long context. So note taking is also useful when the situation demands complex reasoning. Alright, guys, so we've come to the end of knowledge uh, and memory design for agentic system. So in this chapter 6, we've looked at various things. We've looked at RAG system, which are used for building grounded information for the data for the agent. We've looked at search vector stores for retrieval, which uses embedding and vector search to retrieve information from a vector database. We've looked at a context window for short-term memory, where the agent keeps short context and refer to them in order to also generate useful information and to use them in planning and thinking and researching. Then we've looked at semantic memory for personalization, which semantic memory we said it uses chunking and embedding in vector store to generate personalized responses for the user. And then we have the knowledge graph, which are structured information or designed and built using entities and relationship in a graph database, and the agent can use them using a what we call the graph rack to retrieve information. And then we have privacy and governance. So always make sure or whatever you are designing, use the policy. If you are building for a legal system, use the legal policy to build your knowledge graph. If you are building medical system, use medical documents to also build your knowledge graph. And make sure in your whenever you are generating information from any system, use role-based access control, attribute-based access control. Make sure you use minimization. Minimize what you are generating. Minimize the information you are obtaining. Always make sure you store the needed information in the knowledge graph or in the graph database. Do not store useful or sensitive information that are not even needed, for your agentic system design. And in simple terms, knowledge tells the agent what is true. Memory tells the agent what happened. So that is the fact. So thank you guys for listening. Make sure you like this video and subscribe, and